Picking up where we left off last time, we're on lesson number 5, double integrals of separable functions. This really was meant to follow up part 4, where we had a function. I did a change of variables, and it wasn't that much easier to integrate after I did the change of variables. But there was a trick that we missed, and so that's what this section will cover. So if we look back at what we did last time, we had this integral here, which this is what the function was. This was just x, and then we transformed into s and t. So this is what x got transformed into. And then we had, the absolute value of the Jacobian here, and then ds dt. And then I'll rewrite that in this more power rule / anti-power rule friendly form of just each variable to a power. And now if you look at where I've put the square brackets here, so this is the way we tried to do it last time. So I just pretended this is a function of s and t. I'm going to do the partial integral of this with respect to s first, evaluate it at s equals 2, and subtract it, evaluated at s equals 1. But if we look at this a little bit closer, any function of t, since we're doing a partial integral, any function of t is going to be constant with respect to s. So I can move, I have this integral sign here corresponds to integration with respect to s. So the inside integral sign and the inside variable here, they correspond to one another. And anything, and these are corresponding to the variable s, and anything that's not an s is constant with respect to this integral. So I can move that across the integral sign, and I'll get what I have on the right-hand side here. So I get the t to the minus 3/2. That's constant with respect to this integral in here. So I'm going to bring it out front. And now I have something that only depends on s here. And so what this is going to allow me to do is express this integral as a product of two definite integrals that are integrals of single variable functions. So I have here an integral, just of s alone, and then multiplied by an integral on the right of t alone. And so the reason I was able to do that is if I look at this function here, that I can't seem to highlight right now, just get a little bit of it so people can see where the mouse pointer is. Everything in this set of square brackets, I can do that integral, and that's just going to be a real number. And so I can just treat the whole thing, whether I evaluate it and get the real number, or I just keep it in these square brackets, it's constant, so I can bring that across this integral sign here. And now this is going to be obviously quite a bit easier because I can do each one of these integrals independently now. So here I've just computed the antiderivative of the first function, antiderivative of the second function, then I'll have to evaluate them at their limits and subtract. So I'm just using the fundamental theorem of calculus independently now, once for this function of s and once for this function of t. And let's see. So the rest of it's just a little bit of algebra. And I don't suppose anybody remembers the thing I told you to remember on Monday. But it was, so last time it was -6 plus 5 root 2 over 3. This time it's 5 root 2 minus 6 over 3. But because we were able to separate this integral, well, at least for me, I felt it was a lot easier to evaluate it this way than it was to evaluate it trying to integrate it twice as an iterated integral. And so in general, this is going to work only when we have a rectangular domain of integration. So this isn't going to work if the limits of one of the integral depend on the value in the other integral, because then it's still going to have some dependence on the first partial integral will have some dependence, not in the function, not in the integrand, but in the limits. So I won't be able to move that across the other. I won't be able to move that across the other integral. So I have to have a rectangular domain of integration. And then I have to be able to take the integrand. This is the function I'm trying to integrate. And I need to be able to write that as a product of a function of the first variable times a function of the second variable. And then I can express the double integral of f over r as the product of these two single variable integrals. So the double integral of f over r becomes the integral. So remember, this is f, but now I'm going to use the fact that I can separate it into a product of g of x and h of y. And then the AB limits correspond to integration with respect to x, and the CD limits correspond to integration with respect to y. And then because h of y, this is going to be constant when I'm integrating with respect to x, so I can bring that out in front of the integral sign, the dx integral sign. And now inside the square brackets, I have something that I could just integrate and replace with a constant. And so since this quantity inside the square brackets is constant, I can move that out in front of my dy integral. And so what I'm left with is a product of a definite integral with g of x dx and another definite integral h of y dy. And so this was an example of kind of the forward use of this property. So I had a function of s and t that I could separate. It was a function of s times a function of t, so I was able to separate that. It got easier when I did the change of variables because I took my diamond and I turned it into a rectangle, so that allowed me then to use this property. The other thing that will seem kind of strange is that I can also use this backwards. So it's sometimes, and in fact we're going to have a lesson on that in a little bit, if I have two integrals of this form, so an integral a single variable function times the integral of a single variable function, that I'm not able to compute. So each of these, this side and this side, I'm not able to do. When I multiply them together, I am able to evaluate it. So that'll give me a sort of an interesting way to solve one particular problem.